Let us see the half-life equation for the first order reactions. See, we know the rate equation, K is equal to 2.303 upon T log A naught upon A. This is the equation for the first order. Now, let us find out its half-life. We know when T is equal to T half, A is equal to A naught by 2, amount of the reactant left will be the half of the initial one. So what we can write out is K will be equal to 2.303 upon T half log A naught upon A naught by 2. This gets cancelled. It will become log 2. Log 2 we know is 2.303 is 0.3010 and it will be T half. So when we solve all this, you know what we get is, this we know is equal to K. So what we get is T half is equal to 0.693 upon K. So this is the equation for the half-life of the first order reaction, which is equal to 0.693 upon K. So with the help of this, we can find out the half-life of any first order reaction. So let us see this, and now let us move to the graphs of the first order reaction. Now the first order reaction will have a graph between rate of reaction plotted with concentration as a straight line passing through origin, because it is directly proportional to concentration. Now we were knowing, let us see the graph for the half-life plotted with concentration. We know it will be parallel to x-axis because we know the formula T half is 0.693 by K. So it is, this expression is independent of the concentration of the reactants. And we can have one more graph, which is the graph for the integrated rate equation. We know we have done like Kt is equal to, this is 2.303, or we can take the natural log of A naught minus natural log of A. What we can do is we can just shift them. It will become natural log of A naught minus Kt, or let us change both of these logs from natural log to log base 10, and we have to multiply them then by 2.303. So if they are again divided by 2.303, they can be written as log A equals to log A naught minus Kt upon 2.303. So this is what we have, another way of writing down the same equation, and which when compared with y equals to mx plus c, which is an equation of a straight line, give us a graph in which y-axis, on y-axis we put log of concentration of A. We can write it like this, log of A. Plotted, what is the axis? X is the time. What do we get is a straight line which intercepts y-axis at log A naught, and the slope is minus K upon 2.303. So this is what is the equation, a graph from the equation of the first order reaction. Let us see a numerical that how the integrated rate equations can be used. The numerical is of first order. Now the numerical is find the time taken by a first order reaction to get 80% completed if it takes 20 minutes to get 50% completed. So there are two conditions given. Now it says it gets 50% completed, it means half of the reaction is completed. So time taken for this is 20 minutes. So from here we can clearly make out that the half-life of this reaction is 20 minutes. Now from here we can easily find out that the rate constant of this reaction will be 0.693 by T half. So it will be 0.693 by 20, and it will be in minutes. Second condition which is given to us is that It says reaction gets 80% completed in time we have to find out. Now, if suppose initially the reactant was 100, definitely at time t the reactant left is 100 minus 80 because 80% is completed. So 80% of the reaction has already reacted, the reactant has reacted. So how much of reactant is left out? Is 100 minus 80, which is 20. So we can now know that this K will be equal to 2.303. Since the formula we know already it is 2.303 upon T log A naught upon A. So we can use this formula. We can put up these values like the T we have to find out, and it will be what? Log of initial is if 100, the A left is 20. So we have this one. Now these two K are same for the same reaction, rate constants are same. So what we can do is we can compare them like this, that 0.693 by 20 is equal to 2.303 upon T log initial if it is 100, left out is 20. So it is 5. Now we know this will become 0.693 by 20 equals to 2.303. Log 5 is 0.699. We can make it as 0.7 upon T. So when we solve this, what we get is T as 46.5 minutes. So this is how we can use these integrated rate equations to find out not only the time but the amount of the reactant left, the rate constants, specific rate of reaction, etc. Let us see another numerical to understand how these integrated rate equations can be used. The numerical is show that the time taken by a first order reaction to get 99.9% completed is 10 times to its half-life. So we have to show that the time taken by a first order reaction to get 99.9%, which is almost as complete, is 10 times to its half-life. Now we know that the half-life of any reaction is, first order reaction is 0.693 by K. So from here we can find out this rate constant as 0.693 by the half-life. That's the first thing. Second, now if the initial amount of the reactant is 100 and the amount of this reactant which has reacted is 99.9, because this much percentage is complete, we can get that this A is only 0.1, which is unreacted, left out. Now we have to find out the time taken for this. We know the equation, which is equal to K is equal to 2.303 upon T log, it will be what? A naught upon A. So this is how these two we have. Now this equation and this K can be equated, and we can put the values of A naught and A from here so that we can find out this T. Now this can be done as this will become 0.693 by T half will become 2.303 upon T log 100 upon the amount of reactant left was 0.1. Now this will make this as 2.303 T log 10 to the power 3. Now 3 will come out and log 10 is 1. So we know it is 0.693 by T half equals to 2.303 into T upon T into 3 upon T, and log 10 we know is 1. So this is how we can compare. We know this when multiplied will give us 0.3010 divided, it is like this. So the T upon T half is 3 upon 0.3010, which is almost is 10 times. So what we can make out is T is 10 times of its half-life. So this is how we can show this.